Okay, so we're going to talk about Chapter 11, which is about work and energy. And so we need to discuss conservative and non-conservative forces, when mechanical energy is conserved, and the work done on a system both by internal interactions and external forces. So we'll talk about that today. A force for which work is independent of the path is called a conservative force, and that's associated with a change in potential energy, and those forces are reversible. So conservative forces are reversible. That's one of the important things that help you to identify whether something is a conservative force or not. So gravity is an example of a conservative force, because if you think about gravity, you can lift an object up off the floor and then put it back down on the floor, and you won't have changed, you won't have lost any energy in the process. So, and the way to think about for potential energy, if we're thinking about a path, like in this picture, right, an object can go from point A to point B, and they can go along whatever path they want, path A or path B as examples here, and their potential energy change will be the same. So either of those forces can do work on the particle as it moves to A to B, and that'll change the particle's kinetic energy. Non-conservative forces, on the other hand, they do depend on the path taken, they are irreversible. So friction is a great example of a non-conservative force. There's no potential energy associated with friction, right? Remember the equation for friction, for the force of friction, is mu times the normal force. So if we assume that there's no angle of inclination, then our normal force is going to be just the weight, or mg. And so our work is going to be the force of friction. So that would be the first three terms here, mu times mg, and then times delta S. So this is F times delta S. And so the dissipated energy from friction is no longer usable. And so what that means is I can't get that energy and turn that into an increase in velocity or an increase in potential energy. And so both friction and air resistance are examples of non-conservative forces. So in this picture here, you can see that more work is done by friction along the longer path, right? Because if you think about adding up all the little delta S's along the curved path, that's going to be, when I take that times the force of friction, that's going to be a bigger energy loss than if we went by the direct path on the top part of that figure. So if we put everything together, the change in mechanical energy, and so the mechanical energy is both the kinetic energy, delta K, and the potential energy, delta U, that is equal to the work done by non-conservative forces. So that's the mechanical energy is equal to the work done by non-conservative forces. So this means that the mechanical energy is only conserved if there are no non-conservative forces like friction involved. So an example, mechanical energy is being transformed in this picture, right, of the shuttle. It's transformed into thermal energy, right? So that thermal energy would be WNC, right, and that's going to decrease the energy, the overall mechanical energy of that shuttle. So for a system with both internal interaction forces and external forces, we can generalize the energy equation that we see down on the bottom. So external forces do work, and we can identify that as W, or work, EXT, so external work, while dissipative forces do work, and we'll call that W dis. And that causes a change in the thermal energy, which we'll represent by delta E thermal. Conservative systems within the system do work, and we'll call that WC, and that can be associated with a change in potential energy. So putting it all together, if we look at that equation on the bottom, we have delta K, our kinetic energy, plus delta U, our potential energy, plus our thermal energy, delta E thermal. That's equal to our mechanical energy, right? Because that first E, delta E mechanical is equal to delta K plus delta U. And then plus delta E thermal, right? And that's equal to the change in the energy of the system, which is equal to the external work done on the system or by the system and given off to the environment. So that can be positive or negative. So if the system is isolated, meaning that we have no external work, we get the law of conservation of energy. And this says that our delta E of the system is equal to WE external, or that if we don't have any, if WE external is 0, then our system energy, the change in our system energy will be 0. So the kinetic potential and thermal energy within the system can be transformed into each other, but their sum can't change. And also the mechanical energy, E mechanical, is equal to kinetic plus potential, and this is conserved if the system is both isolated and non-dissipative. And this law of conservation is one of the most important principles in physics. And our energy equation can be rewritten as the energy before, that's Ki plus Ui plus W external, is equal to the energy after, which is the kinetic energy K final plus U final plus delta E thermal. And we can represent these by a bar chart here. So sometimes it's nice to think about a bar chart when we're trying to figure out where how the energy has been transformed. So you can see in this picture we have some kinetic energy, a lot of potential energy, and then we have some external work. We're losing energy. The system is losing energy and giving it to the outside. And then after we have an increase in kinetic energy, we have a loss in our potential energy, and then we have delta E thermal. So this is delta E thermal is the energy, the change in energy. So we're not actually we're losing energy with WE external, but we're seeing that we are keeping it in this delta E thermal component. All right, so we're going to stop here for just a minute.